Dr. Babu for accepting Miss last minute request for the lecture. And he already had first lecture on this FDP. So I'm again formally introducing Dr. Aswad Babu from Department of Physics, Triple IT, Dharwad, and he having a vast experience in this quantum sensing and had many lectures in our previous FDP. So, sir, without any delay, I request you for deliver the today lecture, and I request all the participants, please feel free to interact. Please submit your queries or chats. If you want to interact, raise your hand. We will allow you to speak and interact with the speakers. So, if you have any doubt during the talk, do not disturb. Just simply put your message in the chat box. Once we end the lecture, we will go through all the chats and the issue or respond your queries. So thank you, and once again I welcome you, Professor Aswad, for the lecture today.
Thank you, Kamlesh sir. Yeah, once again, a very good afternoon to all the participants here. So we have 1 hour time, so we will just go through what has been asked for to cover. Yeah, I think looking at your schedule, you have something scheduled for today, which is something acousto-electric interaction in nano-dimensional structures. Like our sister mentioned, it may be scheduled sometime later depending on the availability of time. Okay, I hope you have the schedule with you, but I have the schedule. I'm looking at it right now. So, as per the schedule, my session, the second session after the first day session, my next session is implementation with regards to atomic resonances, superconducting Josephson junction, and population inversion. So that I will just push it to today. Okay. So we will have plenty of time to discuss in detail so that if some time if during in my sessions, if time some time extra I get, I will bring in some detailed topics of mine with some plausible implementation, right? Okay, so let me share my screen. And as usual, I would be using my PPT as well as my Blackboard writing. So what you people can do, you can always reach out to me through chat. Like now, the number is reasonably small compared to the big group. So you can unmute with the permission from the organizers and talk to the resource person. So that is one good thing here. So let me share the screen. Yes, you can see the screen. This is what is my PPT, which I would be using. Okay, so let me open it up for our editing. Okay, right. So as you can see, I want to talk about implementation of quantum mechanical principles in physical system, which is very much the key things when it comes to quantum sensing. Okay, so this is in short is like a fundamental principles to implementation. Okay, and if I had to highlight this everything in one statement, like you see in the bottom, I have quantum mechanics initially explained, okay, by using microscopic phenomena, but its principles manifest in macroscopic devices and engineering systems. That's an interesting statement to make. Even though quantum activities or quantum phenomena happens at a microscopic level, the overall effect we will see multiple microscopic systems together probably may form a macroscopic device. From there, we will see the impact or the activity. Okay, that is what all about sensing. When it not computing, I would not talk in terms of computing. When it comes to quantum computing, there probably still we'll talk in terms of microscopic qubits, but here we are going to see from the overall aspect, like collection of many qubits together. We are going to talk in terms of sensing. Okay, fine. So that is what the second statement on my first slide. Let me straight away go to my second slide. Okay, so here you see, from quantum theory to the real systems. Okay, what I mean is theoretical interpretation to real world understanding of quantum systems. Okay, usually the quantum mechanics explains both microscopic and macroscopic phenomena. Here, the classical system fail to describe atomic scale processes. Okay, so let me quickly use my notebook, blackboard writing, and just say what are the things the classical physics rules or a classical mechanics would fail to describe. Okay, that is where quantum mechanics comes into the picture. Let me tell you, till 1900, okay, the year 1900, okay, we had electromagnetic theory, okay, means the theory of electromagnetism, and we had thermodynamics, okay, majorly. And anyway, we have a classical mechanics, Newtonian physics, okay. These are the three major branches of physics were developed till then, and people were thinking everything is fine. Okay, every activity goes around us could be easily explained. So they were known to explain all the physical activities around us. Okay, but till 1900, this was the case. Somewhere just before 1900, okay, what happened? There were few experiments conducted. Few experiments. Okay, few experiments in the sense few things which were not able to explain by these three branches of the physics. Number one, what are those things? Is number one is black body radiation. I'll tell you what is this, and also I'll tell you why we are getting into this when it comes to our quantum sensing course. Okay, so the black body radiation. Number two is photoelectric effect. Okay, 1 minute. Number three is atomic resonance. I would say atomic stability. Let's say in terms of stability, atomic stability. Okay, so these are the three basic things or three basic experiments were conducted just before 1900 by some experimentalists, and they got some interesting, intriguing results. Okay, some experimental results. Okay, and that's fine. The experiments were conducted, results obtained. But the problem is the experimentalist asked the theoretician to please explain the results. Okay, we make the experiments. Experiments, anybody can do the experiments, right? Carefully, they have to do. But when it comes to analyzing the results, okay, they, the experimentalists, ask the theoreticians to please explain using the existing physics rules or facts. Okay, the physics theoreticians started explaining the results using these three branches of the physics. Okay, one such a thing is black body radiation. What is a black body radiation? Is if you just take a solid, any metal, you heat. Okay, if you heat a solid and see what is the energy radiation emitted out of that hot solid, if you plot the frequency versus intensity, what you see is a continuous band of spectrum, like for every frequency there is an intensity. It's like a bell curve they saw. At the same time, they put some gas inside a small three-dimensional box. Okay, and they put the box inside the box, the walls with a nice metallic film, and they filled the box with some gas. Okay, they started heating the film, the walls, and the walls ultimately heats up, and they heat the gas inside, and they put a small hole and started seeing what is the light coming out from that particular hole. Basically, when it comes to heating mechanism, here also they're heating the solid. Okay, right? But the problem here, when they saw the spectrum of light coming from this hole, they did not see a continuous spectrum. What they saw, a band of, like not a band, a discrete spectrum. For a particular frequency, there is mu1, and some frequency there is another light source, like as if there is some colored lines. Okay, red, blue, green, something like that. So this is a discrete spectrum, this is a continuous spectrum. Okay, both the places heating is done in the same fashion. Okay, and this is the one experiment. Okay, the number two experiment is, number one experiment is black body radiation. They call light coming out from this box, light's called a black body radiation, BBR. Why is that so? Black body radiation for us means what? It absorbs everything and doesn't emit anything at all. It's a black body. Like say in summer, if you just take a black body, you see that. Okay, 1 minute. I'm sorry. Okay. So here, if you see, the black body radiation is discrete when it comes to gas, which is being heated inside. When you heat a clump of solid like a metal, if you heat it, you get a continuous spectrum. Okay. So now we have all the understanding. That's why we are directly able to distinguish. But back then, there was no, there was no spectrum idea. All these things were not there that time. They saw both of the things as the same process, and they were not able to distinguish. And by the way, why the spectrum is increasing and later it is decreasing? Why is that so? All sorts of questions were asked by experimentalists to the theoreticians. And also there is one more experiment is, they took a metal and started hitting the metal with some light source. Okay, and if the light source frequency of particular frequency, if it, if they start increasing that frequency, okay, let's say they started increasing frequency, and at some frequency they got to see like a fixed frequency, let's say, let's call mu r. For that frequency they have started seeing electrons emitting out of that metal. So electrons are emitted. Okay, then they thought, okay, electron is emitted, which means if I increase in frequency means what? If I multiply the frequency with the Planck's constant, you get energy, you see. So if I increase the energy, obviously the frequency of electrons emission would increase. So they started increasing the frequency. But as you increase the frequency, electrons were not emitted. That is strange, right? If you increase the energy, it should emit, but it is not increasing. So they were not able to understand. And what they did, instead of increasing the frequency, they started hitting with a particular matched frequency, mu r, few more photons, like say multiple beams are coming and interacting. It's like increasing not the frequency, increasing the intensity of the light. What I mean by increasing the intensity of the light is, with the same frequency many photons were coming and hitting the same surface. That time they started seeing multiple electrons coming out. Okay, it's something puzzling to them. So this is actually called photoelectric effect. So it is asked by experimentalists to theoreticians, why is this so? You will see now how it is connected to our atomic resonance as a topic of today, and also other things. And there is a third experiment. There is no need to do the experiment at all. It is there occurring at every point of the time. This experiment. What is this experiment? Is if you just take a atom, any atom, this nucleus is there. Let's say one free electron is there. That electron keeps revolving around the nucleus continuously. Okay, and see, it is being attracted by the nucleus with some force of attraction. Okay. See, when something which makes a continuous work, it has to lose energy. So the electron, when it starts losing energy, okay, ultimately it has to get attracted by the nucleus and it has to come down and fall into the nucleus because nucleus is always continuously attracting. Okay. A simple analogy if I give you, if I ask a student, a particular student, to go and make a rounds in the about some point, you make rounds about the in the ground. So he initially he may start running. He continuously runs. After some time, what happens? He loses the energy. He may decrease the radius of the circle, and then after some time, if you ask him to run from morning to evening, what happens? At the night, by the evening, he may come and fall into the nucleus at the center of the nucleus. Okay, what happens? That is not happening. Electron is never ever losing the energy despite doing several running around the nucleus. Okay, so no loss of energy for electron revolving around the nucleus. Okay, why is that so? So this is a questions asked by again experimentalist theoreticians. Okay, so theoreticians started explaining these three processes using some existing theory of physics: electromagnetic theory, classical physics, which is Newtonian mechanics, thermodynamics, which talks about heat and how it transfers from whatever is there. So multiple physicists and mathematicians, okay, those who are versatile in both the field, they came along, they started explaining the black body radiation process. Okay, and some of them were able to explain why is the light intensity increases at a very initial level. Okay, so it is right, let me call a different color. Okay, so what somebody explained at the initial level, someone started able to explain at later level. Okay, so Rayleigh Jean and Wien, these are the two people. One person explained as starting and another person explained. Rayleigh Jean and Wien, but both of them were unable to explain the entire curve. So the in between middle range frequencies, they are not able to explain why is that so, why it is peaking and then decreasing. Okay, so that is a failure, but they have started a very good initiation. That is the time Planck came along. Planck, he said, he gave a very intuition based theory. He said radiation never will transfer in a continuous fashion, it always transfers in a discrete fashion. What is that discrete is? Just like we have in the material, the smallest material as of now, we can have, let's say, electrons or protons or subatomic particles inside the nucleus. In the same fashion, the fundamental starting unit for energy or the radiation is a photon. So he introduced photon, the idea of photon as he introduced the idea of photon as a fundamental property of energy. Okay, it's called a pocket of energy. Okay, and its value, energy value, is just simply Planck's constant multiplied by frequency with which the energy is radiated from a particular source. Okay, he said if the radiation is traveling from some source, basically we see a photons traveling. Okay, for us, for a naked eye, it may appear to be a stream of light, but what it is actually a bunch of photons traveling along. Okay, if I'm increasing the intensity, which means I'm increasing the intensity, I mean, increasing the number of photons. If I'm increasing the light source frequency, means I'm increasing the energy of a particular frequency. Okay, so that is what he explained. The moment you bring the idea of photon, the pocket of energy, discreteness, energy transfers from one point to other point in a discrete form. So the moment you use a Planck's idea, so you can easily explain, you add a Planck's idea to relay gene and Wien, you are able to explain the entire curve. Okay, so the entire curve is being explained by Planck's radiation concept, and why is the discreteness also comes from the light, also easily explained with the Planck's idea. So you take, let's say, helium in the gas, the helium atoms just excite at some frequency, de-excite means comes down and they emit the light. So that particular frequency is only emitted with some just one line with a spectrum, just like one frequency. Similarly, let's say nitrogen. Nitrogen and helium, all those things would emit with single frequency. So this is how Planck was able to allow like understanding the black body radiation. Using the same spark created by Planck, Einstein came along. Einstein said, the moment you bring in the idea of the photon, a discreteness of energy, means to have multiple electrons coming out of the atom or a material, what should I do? I should send a frequency of the light or the photons in such a way. If the material is having a transition frequency from their ground level to excited level, if the incoming photon frequency exactly matches with this transition frequency, then I see electrons emitting out of the atom and out of the material. That is where I see photoelectric effect, electrons being emitted out of the material when I hit with a specific frequency and slightly more in the energy. To have electron travel out of the atom, I have to give something called work function. Okay, not only just knocking out of the atom, just go travel beyond the atom, we need to give slightly more energy. But what matters more is matching the input frequency with this transition frequency of the atom. Okay, so that is done. And next thing is why atoms are stable, why electrons are not falling into the nucleus. Okay, taken the idea of Planck, right? Bohr introduced the idea. It's like it's what he introduced the idea is there are specific orbits for a given atom. So in those orbits, the angular momentum is quantized, energy is quantized. Angular momentum. What is the momentum? The momentum for you is mass into velocity, linear momentum. If you multiply it by radius of the orbit, mvr, okay, you see always radius and motion always perpendicular. Okay, motion, translational motion is along the tangent, so it's perpendicular. So usually it is mv cross product r, but both are perpendicular, velocity and r. So what I don't have the angular between them is 90, sine 90 is 1, so I straight away write mvr. Okay, so this is always quantized. What is this quantization is? This value of mvr falls in some units of Planck's constant. If such a units of Planck's constant like matches or the orbits exist with such an angular momentum, boom, we can say if there is any electron moves in that orbit, this guy never ever loses energy, as if he just revolves in that orbit without losing energy. So because of this, there are orbits exist around the atom with such a quantization values. That's why the electrons never lose. That's why electrons are remain stable in that particular orbit. In order to move out of the orbit, you have to give a energy just like photoelectric effect. Okay, so this is the first principles or the facts of quantum physics started, and I would say it's a birth of quantum mechanics or a quantum physics. Okay, here you see the topic of resonance is there, topic of atomic spectrum or optical spectrum is there. Okay, and there is only one part which is missing from our title. Okay, what is missing from our schedule is Josephson junction, which is also quantum effect, by the way. Okay, so let's get into the PPT which I had. Atomic resonance is there. We just discussed. What is atomic resonance? You send the input frequency matching with the transition frequency of the atoms which we have chosen for exposure. Okay, right? So that is the atomic resonance. And the other thing is something Josephson junction we will just discuss as we go through this PPT. And the third one is something called the extension of atomic resonance is called population inversion. Okay, so these are the three things which we are supposed to discuss in this PPT or this session. We will do one by one. Okay, so let me go further. Basically, all these three phenomena are the manifestation of quantum mechanics for you. Okay, let me see if there is any questions on this so far. Okay, looks like there is no questions whatsoever so far. Okay, right. So, what is atomic resonance? The basic concept of energy quantization. It is okay. So here I have for you a nice picture of description. You see carefully. If I have a nucleus inside an atom, which is somewhere here, and its orbits are something like this. Okay. So every time I'm not able to draw the entire atom with the circles and the orbit, what do? I just ignore and write only part of it. Okay. So what I'll do, I'll just ignore and just draw a lights. So the E1 stands for energy associated with the ground state orbit, which is very close to the nucleus. And E2 stands for excitation, slightly away from the orbit. So if an electron happen to be in that excited state, means it is going to have extra additional energy over its ground state energy. Okay. Now if you see, right, if I supply a photon of energy matches with the exact transition frequency, what happens? Electron go and jumps under excited state. Okay. So that is a absorption for you. Okay. But by any means, if already electron is existed in the excited state, you know what happens? Okay. So the incoming photon, see, whenever somebody is already ate full food, okay, and if you offer him something, he will say, I am full, I will not going to have. Okay. So at microscopic level, this is not the scenario. It is slightly different. I'll tell you, this is not going to consume for sure because the electron is not allowed to go anywhere else other than first and second orbit. So it is already there in the second orbit. Whenever a photon is incident, what happens is the incoming photon, this guy, right? This guy has no job, nothing else to do here because he is no more needed here. But you know what this guy does? This guy somehow just triggers a stimulated emission from this atom such a way the electron is just a trigger to come down to the ground state, and when it comes down is existing with a higher energy earlier. That energy is also emitted along with the incoming photon. So this is called stimulated emission for you. Okay. So by on its own, if some excited electron comes down on its own, usually what happens if there is an electron in the ground state, if I excite with the photon matching with the frequency of the transition, so this guy will go and excite and stay in the excited state for 1 microsecond. After 1 microsecond, this guy will comes down and he will emit the same frequency of the photon which he observed in the first place. So this is called a spontaneous emission for you. Okay. But if by any means the electron is already in the excited state, if I send a photon now, it creates a stimulated emission. So the stimulated emission is a very interesting stuff. What you can do, the emitted photon from the electron de-excitation, that also can be put to go in a particular direction as per my wish. If I let the electron to emit on its own spontaneously, that time I have no control over which direction the electron can emit. It just emit on its own at any direction. I don't have any control. In order to have a control, I have to streamline things bring the things into control, I'll go for something called stimulated emission. Okay. So along the process, along the process, not only send a single photons, I will send a bunch of photons, let's say separated by some time. Okay. Some pulse of photons if I send, what I can create the electron to go back and forth between the ground and excited continuously in resonance, in sync to my input frequency. What I mean by resonance here, you please imagine, take the analogy of somebody playing in the park with a swing. Okay, so what happens if you just play with the swing, right? It's continuously going back and forth. Let's say you are standing at the end, you are just giving a push to the swing. Let's say your kid is playing, so kid is in the swing, he just go away from you, comes back to you. You just above, when he about to comes to you and he is about to change his direction, exactly that is the time unknowingly you give a push to the swing. So what you are doing, you are giving your energy or a transfer of force to the swing in a sequence, like a every periodic movement you just give tap tap. It's not like when he is coming towards you, you are not hitting abruptly. You are just wait for he's about to stop. That time you will give the push. So what you are doing, you are giving a push in sync, in resonance. In that way, you sustain the oscillations continuously. If you don't do it, you know what happens? The oscillations will comes down due to the damping. That will not happen if you do the extra force. If you had that time, you can increase the oscillation continuously with an amplitude. So that is what the simplest analogy to understand the resonance. In the same fashion, you are going to put your frequency of photons in sync with the electron transition continuously happening between ground and excited. This is how you can make the oscillations of the electron. So this is called a Rabi oscillations. Okay, right? So even using this concept, you are going to create a superposition of electron being in the ground, electron being in the excited. It is also called a quantum coin. Okay, it is just like you take a coin and flip it. During the coin flip, you see flight time, I see both head and tail the same fashion. I see electron being in the ground and excited continuously in a first form, in an ambiguous form, which I can't exactly specify whether it is in the ground or excited. It appears to me like in both the places. Okay, so this is the resonance for you. What I have to do to put the things in resonance? Very simple. The incoming photon frequency should match with the transition frequency. Okay, delta E, the transition frequency, must be equivalent to the incident frequency of the light, that is a photon energy. Okay, the moment you do it, you put everything into the consideration of resonance. Why is so important for us? Because I want to create a qubit out of it. Okay, so qubits are very much needed for me for a computing, or when it comes to sensing. If I create a qubit which is sensitive to the external fields like electric field or a magnetic field, if their superposition is going to disturbed by external electric or magnetic field, then boom, I am able to create a probe out of it. So people started creating a probes using these such qubits. One such a thing is the NV center qubit. Okay, right? So that is what the for atomic resonance concept based qubit realization, and then a sensor or a probe based on the qubit. Okay, so this is atomic resonance for you. Why is so matter for us? We need to understand this to understand our sensing. Okay, so as time progress, there are various sensors that are going to be like discussed in this particular module. You will able to appreciate with the foundation what is being built today. Okay, so fine, atomic resonances. And the next thing is, okay, the spectra. What is atomic spectra or any spectra, optical spectra, I mean. Okay, right? So let's say you just concentrate here. There is a plot I have for you. You see, there are multiple curves. One is very bell curves and very lenient peaks. Okay, these are things which I have it for you. Let's say I have a laser. Laser by nature, very few frequencies are will be there. Fixed frequencies, like red color light, red color laser, or a green color laser. Only one single frequency is there, will not be able to draw the frequency spectrum of that frequency of that particular coming light in a single line. You know why? The small deviation from the actual value from omega to slightly omega. You see, laser is supposed to have a single frequency, but due to some other factors, there is a small delta W, small variation. So I would have, instead of single frequency, I'll have a peak, something like that. So that is what this laser line width I have for you. Okay. Now, if I make the light, like laser light, to be absorbed by some collection of atoms, they call us atomic plasma or vapor, atomic vapor. Okay. The plasma, okay, inside that plasma, there may be atoms are there or ions are there. Those things may absorb the light, just like I showed you. They excite and then de-excite, they emit the same light. Okay, this the if I induce some stimulated photon emission, i'm able to see a nice spectrum, absorption spectrum for that medium. But there is a problem, not a problem, there is some catch in the medium. If it's a medium, if you take atomic vapor, atoms, you see, atoms are not stable, or ions are not stable in this gas. They may just going here and there, some of them going away from the laser light, some of them are coming into the laser light. Because of this motion, they all the atoms would not experience same amount of frequency. You know why? You just see, if you're standing in road, let's say a vehicle ambulance comes very close to you, that time you hear a lot of sound. As it recedes away, you see less sound you are hearing, even though same amount of light, sound is being created, but what is coming to you is reduction in the energy. Okay, the wavelength may be more, energy is less, frequency is less. Due to that, all atoms are not going to see same kind of a frequency, they are going to see different frequency. So some among the laser spectrum, okay, with some line weight, okay, so all the atoms would absorb that spectrum. Okay, so that is what you see due to the Doppler spectrum, right? So there may be all the absorption of the input light. Okay, not only that, there is also something called collisional broadening. Means atoms come and they hit each other, they exchange the energy, and their absorption spectrum also changes accordingly. Just like Doppler broadening, the energy spectrum transition frequencies of the atoms also, some of them changes. Due to that change, it's not a disadvantage in a way. They also allow the spread laser frequency to be absorbed. Okay, right? So even the line width is small, there is absorption throughout entire line width. So usually the absorption spectra, what is given here is a green color. Okay, so this is something like this, green color, and due to collisional broadening, the spectrum just broadens slightly. Okay, so I might have more atoms with a wide other valuable frequencies. Okay, in that way I can cover the entire spectrum of the line width. Okay, so that is atomic spectrum or optical spectrum for you. So how it is going to be useful when it comes to quantum optics or any optical experiments is, let's say I have a material. Okay, I don't know what is the chemical combination of that material. Let's say in the chemistry there is a lab, liquid is there, I don't know what is consisted in it. You know what I do? I just incident that liquid with a solution with some laser light. I just take out emitted light and study the emitted light. So that is atomic spectroscopy for you, or a optical spectroscopy for you. So it is actually using the idea of resonances. Okay. And when it comes to NV centers, which I just told you, we can have a qubit preparation inside a nitrogen vacancy centers. So this vacancy centers acts like a qubit. There, in fact, can be put in resonance with the microwave pulses. Okay, right? So these resonances can oscillate. The oscillation can be with the microwave pulses. In that way, you can have a better control on the on the superposition state. So which can be used for later sensing purpose. Like I said earlier, you would come across this when you started saying various kinds of sensors in this module. Okay, so quantum control is possible in the solid state materials like NV centers. Okay, nitrogen vacancy centers in carbon, optical spectroscopy just to understand a particular material combination from the spectral lines emitted by that material. Okay, so the another important thing as a part of quantum sensing comes in, it's called atomic clocks. What is this atomic clocks? What is so much important is about? Yeah, I'll tell you what, if you just take an interesting material like a cesium isotope 133, okay, if you take a cesium 133, there is 54, 55, sorry, 55 electrons in this material, okay, 54 of them are paired. Okay, so which are paired inside 6s orbits. 1s, 2a, 1s, 2s, 2p, 3p, and so on. Orbits are there for any atom in the same way cesium has. So 54 electrons are of them occupied inside this 6s orbit. Exactly at a 6s orbit, there is one electron, unpaired electron is there. That is the guy who is makes a lot of magic. Okay, if that guy, if I expose that guy to some excitation energy, you know, that guy is going to excite from ground state to excited state. Okay, right? So he will jump, and he will jump only in a particular frequency whenever transition frequency matches, the transition frequency matches. Okay, now if I take a cesium material in a given time, if I incident a particular light source matches with the transition frequency, only certain number of atoms gets excited in a given time. Not like abruptly everybody gets excited. It's not like that. So as you incident the photon, then you see a transition frequency is happening between ground and excited. So at a given time, if I take out the light coming from that transition absorption spectrum, what I see, there is a nice spectrum coming out. Okay, so in a given time, how many such spectrums are coming? Or in a given time, how many such cesium atoms are exciting? You can easily count by counting the wavelength or the frequency of that kind outcoming light. Okay, so by doing it for a given second, it's always fixed the cesium atom, cesium material for a given second. Only something around 9 into 10 to the power of 9 transitions, excitations would occur. That is fixed. Right? You do this experiment here or anywhere, it is always fixed in that way. So you can go on to create atomic clock using this cesium. You take a cesium and then hit with the light, so you can keep counting. In 1 second, this many happens, right? In fact, what is 1 second for you? If somebody asks what is a 1 second, you usually give how much time I will take to close my eyes and open. You flick my eyes and open. That is 1 second for you, right? That is the closest simple description you could give for 1 second. But if I had to give a scientifically, what is a 1 second for you is, if I expose my cesium atom with the light, incoming light, with the matching transition frequency, I would see something like 9 to the power of 9 excitations of the cesium atoms. So that is how 1 second of a time is being defined. Okay, so since these transitions are very much accurate from place to place, doesn't get affected by anything, so what people thought, can we create a clock out of it? What is a clock for me? It is something which ticks. For me, 1 second is the time I take to close my eyes and open. That is 1 second. Okay, right? So in a given second, this many transitions would happen. People thought, okay, I'll create a clock out of cesium atoms inside a material, and then incident some light and start counting how many excitations are happening. From there, I will just count a time. Okay, so that is atomic clock for you. In fact, this is a part of your quantum sensing module. Okay, so let's go further. The next thing we're supposed to discuss as a part of this module is Josephson junction. Okay, so what is this Josephson junction is? Josephson junction is a simple material, in a way complex. I would not say simple. You take a superconducting material on one side, you attach insulator, superconducting insulator, and then again superconductor. And please remember, when I have a superconductor material, what I mean, it would create a zero resistance to current going through it. Means it executes zero resistance to current going through it. But it is impossible to have at room temperature. You know why? At room temperature, electrons inside a material are always excited, or at some excitation will be there. They're slightly held to the nucleus at the outermost orbit. If there is any rules possible energy supplied, they come out and they create some kind of a hindrance, or the existing ions there after electron coming out, they also create a hindrance. There is a lot of collisions may happen when I connect a material to the any resistance conducting material to the battery. I see heating up, okay, as the electrons start colliding. Okay, right? So, but if I take a material, a superconducting material, if I cool it to absolute 0 degrees Celsius, means a temperature is so small, at that point there is no possible energy supply for any electron inside a material to have. At that temperature, you know what happens? The electrons may not be coming out. At the same time, if I add some external voltage difference to the material, I would not feel any collisions for the electron traveling through the material. So I would say zero resistance is exerted or manifested to this traveling charges inside the material. Only the superconducting particular kind of materials would have such a thing. Okay, that is a perception, intuitional way of seeing things. Okay, please remember it is not the actual picture. What is the actual picture is, if I take a superconducting material, what happens is usually the electrons comes out of the atom when there is a voltage difference is added through some battery. So electrons come out of the atom, they travel. When they travel, they get hindrance due to other ions collisions along the path. But if you cool it, you know what happens? They may not see any collisions whatsoever. They travel very smoothly. Why they will travel very smoothly? Because they form an interesting, a kind of a pair. It's called a Cooper pair. What is the Cooper pair is? From an outside, if I see the electrons, they appear to be bunched together like a pair. Okay, in fact, electrons cannot be bunched together. You know why? They are of opposite charges. They're not supposed to have same kind of a attraction. At the most, I can have electron magnetic movement. Due to magnetic movement, they can attract. You know why? So let's say take an electron, which is a negative charge particle. If it revolves in such a way, it current is anti-clockwise, then a magnetic moment would be north and south equivalent. If an electron is there, if its current is revolved in such a way in a clockwise direction, its corresponding magnetic momentum would be opposite, which is south north. Now, such electrons you bring, it's like two bar magnets in opposite manner. If I try to bring the attract in a same format, like a north-north, if you try to bring together, they repel each other. That is what the electrons usually. If magnetic momentum wise, if I bring electrons in an opposite parity in their magnetic moment, they attract. So in that way, I can create a pairing. That is what pairing happens inside an atom in a particular orbit. They say paired electrons. That is happens in an orbit. But when it comes to superconductor, you know, it's not that kind of a pairing. The pairing is slightly different. What kind of a pairing is? So I'll tell you a simple analogy. Let's say there is a corridor in an institute. Let's say corridor is there. So corridor is there. The corridor has a very small exit, small door, but corridor is very big. So let's say at a time the classes are ended, students all come at a time out of the classrooms, travel through the corridor. When there is a plenty of space, you see, they travel very smoothly because plenty of space is there. I see from the very distance that students are traveling, it appears to me they are going very, very far from each other. But when it comes to exit point, they have to slow down. Only one person can exit at a given time. In that case, what appears to me is electrons at the exit appear to go in bunches together. People are going in bunches. If I don't see the corridor, if I just see at the exit, I see, oh, there are two friends traveling together. Like that. That is an impression created to me. In the same fashion, I can create such an exit. Okay, something like there is a very free space, there is an exit, there is a free space, there is an exit. So if the electrons are traveling very smoothly, when it comes to exit points or the very close points, they travel together. Other places they travel far. And when it comes to exit or a small places, they travel together. So what I see, Cooper pairs are formed something of that kind. So they may not be attracting each other, they're bunching together due to the structure of the material at a very, very low temperature, like absolute zero. So that is what the Cooper pairs are. Why they will be created? Because of the cooling. Okay, so usually the electrons are excited, they travel. Okay, when they're excited and travel, there's some kind of oscillation frequency they will be having. So if I have two kinds of a material, left side and the right side, so I can always write down what is the wave function for a given set of electrons inside a particular material. Okay, so quantum mechanics says whenever things are microscopic, I cannot describe them using a position and a momentum in a given time. I have to always describe them using a wave function. Wave function is something which tells me about the material at microscopic level. From the wave function, I take the absolute square of the wave function. Okay, if the wave function is some sinusoidal function, I take absolute square, I'll get a hill kind of a structure. From the wave function absolute square, I can make out where that microscopic particle is existing, like an electron. Okay, so the bunch of electrons which were combined due to this cooling at the absolute zero, on the left hand side, if I try to find what is a wave function corresponding to that, it will be wave function some magnitude multiplied by some sinusoidal function which is exponential I phi, where phi is a phase with which oscillations would happen. Okay, right? Now that is one side. The other side is also, there is another set of frequencies. Okay, another set of oscillations will be happening. Okay, now why is this happens? Probably I might have connected this to some battery. Okay, now see, on the left hand side I have a particular frequency of oscillations, on the right hand side I have a particular frequency of oscillation. Due to this, there is a phase difference always exists. What is the phase difference? There is a delta phi is equal to phi 2 minus phi 1. Let's say phi 2 is on the right, phi 1 is on the left. So this kind of a phase difference would exist. Because of this phase difference, currents even tunnel through, the electrons tunnel through this insulator. You know what is the role of insulator? No excitations whatsoever. Nothing can penetrate through this insulator. But because of this superconducting material, the Cooper pairs are formed. They become so powerful, they can tunnel through this insulator material. Tunnel through means they can punch through. Please remember, in terms of material, we see tunnel means, let's say, train going through a hill through the tunnel. That is what the tunnel for me. But when it comes to electron, how electron tunnel through on a hill? Very simple. Let me give an analogy. Let's say there is a hill, potential hill. Okay, if I have an electron send towards the hill, what is the hill height? Let's say hill height some v naught. Electron, it doesn't have that energy. Let's say electron is having only energy. In terms of energy versus energy on the y-axis, if I plot position of the electron, in order to cross this hill, the electron must have the energy more than v naught. Okay, incoming energy. But electron is a material, it's a microscopic material. At a microscopic, I will have both wave as well as particle nature. So if I talk in terms of wave nature, it is actually having a wave, something like that. Okay, when this wave hits a hill, even though hill energy is much more than the wave energy, you know what happens? There is a possibility to wave even exist inside the hill, but lower level. The intensity may be lower level, and even beyond the hill also there is a possibility of electron existing in terms of its wavelength. Okay, you see there is a diminishing of wavelength, sorry, wave nature inside a hill, and beyond that probably they may be decreasing, the wave nature is being decreasing, but you see the presence of the electron in terms of probability amplitude, it is there. So that is what the electron tunneling through the a hill, or uh, tunneling through or going through the hill presence in terms of wave nature. Okay, right? So due to that kind of a tunneling, you see the electrons just punch through a insulator, goes to the other side. They are not keeping quite on the other side because the other electron pair is also there. They will punch back into the material to the left side. So basically what you see, electron pairing up pairs of Cooper pair and go back and forth. You just concentrate on one of them, they are going to have a particular frequency. What is that frequency? That frequency is directly equal to the rate of change of phase, delta phi. Okay, phase always keeps changing because I am connecting that to a battery, let's say. Okay, so from that, basically what I'm creating, let's say, high potential, positive V, negative V. Like if you take something, some plate, you put some ball in it, you just raise on the other side, the ball will travel from high to low potential. In the same frame, you just create high potential and lower potential in this Josephson junction. You see electron punching back and forth continuously between these insulators, you know. Because of this, I'll have a current. From there I can make some induction effect, and I can use this for something called a qubit realization in terms of artificial photons. That will be discussed later. For the time being, what is a Josephson junction for you? It is a material or a junction created of a superconductor and insulator bunched or sandwiched together with the insulator in between. There the Cooper pairs punch through the insulator with some frequency which is directly proportional to the voltage applied, and the electron charge is there, Planck's constant is there, nothing else. Okay, so in a way this is equivalent to having an induction effect, some inductor in a circuit. Okay, right. So whereas Josephson junction is used in squares, it is used in artificial atoms, that is superconductors, sorry, transforms artificial atoms. So IBM uses in their chips this superconducting qubit based qubits, okay, and some voltage standards. Josephson junction define the voltage with quantum precision. So if you want to define a voltage, what is one voltage for you? If you want to define, you can use this. Just like how we will count the time, okay. So the last concept is population inversion. I'll just take 2 minutes, then I'll just conclude. What is a population inversion? So I can, instead of taking a 2-level atomic system, I can take a 3-level atomic system. In such a way, I can just excite the electron directly onto the excited state and make that to a de-excitation into the mid-level, and I can stop de-excitation from mid-level to the last level. I can stop. In that way, I can put the electron trap in that mid-level. Okay, so if I trap it, what I'll have more electrons here, less electrons at the ground. So basically, it's called population inversion. Population inversion is very important key for, for having a laser effect. So basically you are playing with the transition frequencies. By external means you can control which frequency to occur, which frequency to be forbidden. In that way you can trap the electrons in a particular level. So that is what population inversion created out of 3-level atomic systems. Okay, right? So you can't have population inversion to 2-level atomic system because there is always equal probability of equal electrons in the ground and excited. You can't go more than that. So to have more electrons on the excited, less electron on the ground, you need to go for 3-level atomic system. First I excite to the higher level, de-excitation I trigger to the mid-level, but no de-excitation from mid-level to the lower level. I can stop that, I can have more electrons, and I can have a lasing effect between mid-level E2 to E1. So that is how lasers are actually constructed. Okay, so that is the population inversion for you. Fine. So 1 minute. Okay, so lasers, how they are constructed, here you can see in my PPT, right? So comparison of these key phenomena, which are very much important for our qubit realization. In the case of sensing, atomic resonances and Josephson junction and population inversion are talked in terms of different things. For example, principles, quantum principles, what is a key description in terms of mathematics, how it is being implemented, and what are the applications is given here. You can go through it later. So the conclusion is the coherence. How does the coherence scale is enlarged in systems, we just discussed. What are the limits for quantum control in practice, we just discussed. How can we use these principles to drive future quantum devices, we will see as you people go through this entire quantum computing sensing model. Okay, so I'll just stop at this point. I see no questions in the chat box, so nevertheless, if you happen to have some questions, keep it for yourself, or you can share with me, or you can ask me in the next session, which I'm going to come and continue where I left off in today's class. Okay, so once again, thank you very much for listening, and I thank Avasti sir also for the one opportunity to discuss these things. So I
No,
quick over to Avasti sir. He can take over. Thank you, sir.
thank you, sir, for your time and today lecture. So let's see if there is any questions in the chat box. Mm.
No, sir, there are no questions, so we can proceed.
So in this situation, I will thank the speaker, Dr. Asad Babu sir, for the time and for the lecture, because I think our next speaker have already joined. So, sir, I will go for the next talk. And once again, thank you very much and for joining and for the lecture. So let us welcome our another speaker for today's session, Dr. Vaibhav Gupta from Center of Quantum Science and Technology, IIT Mandi. And he already had a few lectures earlier. So today he's going to talk on photonic quantum computing. So I request Dr. Vaibhav, please continue the presentation.
Thank you, sir, for the kind introduction. So, good evening to everyone, and let's begin today's lecture. So, today we will talk about photonic quantum computing or photon based quantum computing. This will be the topic for today's talk. So, I will give you a brief overview about the classical computing, and then we will try to switch towards quantum computing. And in the quantum computing, we will go particularly in the case of photon based quantum computing, and then we will try to discover it. So let's try to build a classical computer. So in classical computer, we always represent things in terms of bits, so 0 and 1, right? For example, if you want to represent a number, so 1 can be written as 0001, or 2 can be written as 0010. So in terms of 0 and 1, you can write numbers, right? Similarly, you can write characters also. So if you have A, the corresponding decimal will be 65. And then you can write a code 01000001. That's called ASCII code. It's an 8-bit code for character A. We can do the same exercise and we can also write about B, C, and D, right? So not only the numbers, we can also represent the characters in terms of 0 and 1. Not only the character, we can even write a complete name. So Vaibhav can be written using this ASCII code, and you can write Vaibhav like this, right? So what are these 0 and 1s in a classical computer? So basically it's like a switch. So if you have 0, you can switch into 1. If you have 1, you can switch back to 0. And this task of switching between the bits is being done by transistors. So if you remember these BJT MOSFET transistors, so these kind of lot of billions of transistors are there in your chip or motherboard, and they perform these kind of 0 and 1 task. How this happens? So if transistor is in off state, you will call it as a 0. If your transistor is in on state, you will call it as a 1, right? So that is the 0 and 1. Now in a classical computer, we can store memory also. So you can store the memory in terms of 0 ones. Then you can flip between 0 and 1s using your transistors, and you can also do AND gate, OR gate, NOR gate, NAND gate. These kind of logic gates you can perform. And this also you can do using transistor. So transistor becomes the main key in our classical computers, right? Now let's try to see a quantum computer. So as we remember, in classical computer we have these bits, right? So if it is 0 or it is 1, depending on whether we have applied some voltage to this gate terminal. If not, then it is 0. If we have applied some voltage, it certainly becomes 1. So we have two discrete bits like 0 and 1 in case of classical computer. As soon as we switch to quantum computers, we do not have discrete 0 and 1. What we have is a quantum superposition. So what you write is you have alpha times state 0 and you have beta times state 1. That is the case when you have not measured anything, right? As soon as you measure something, this state will collapse either with the probability of alpha square and it will go into 0, or with the probability of beta square it will go back to 1. But unless you have not measured, you always have this quantum superposition, that the information is available in terms of superposition of 0 and 1. But this facility was not available in classical computers, right? Now we know that this bit job was done using transistor in case of classical computer, but who is doing this job of qubits? So the job of qubit is done depending on which kind of quantum computer you are trying to build. For example, some qubits, we call them natural qubits because naturally they are there. So we have the light. This we have not created. We already have photons given by the nature. So if you are using photons as a qubit, we call it a photonic based quantum computer. If you are using trapped ions as a qubit, we call it as a trapped ion based quantum computer. Now, each of these different domains have their own advantage or disadvantages. For example, this trap ion based quantum computer, here control becomes very tricky because you are using multiple lasers to control the qubits. And the operation, meaning the gate operations, are also very slow. As compared to this, the photonic quantum computer is quite fast. But it has its own disadvantage due to decoherence, and the trapped ion ones also has decoherence disadvantages. And there are different companies. For example, IonQ is a very big company working towards the ion based quantum computer. Similarly, Xanadu and Psi Quantum, they are using photons as a qubit and trying to build a quantum computer using photons, right? Those were natural qubits. We also have synthetic qubits, meaning we have created the qubits. So for example, you can also use superconducting. So you can use Josephson junction and use them as a qubit. You also have silicon based quantum dots. You can also call trapped ion as a synthetic qubit because you have to create ions. The another example is topological qubit or diamond vacancy center. So again, there are multiple ways you can create qubits, and then depending on the system you are using. So if you are using superconducting loops, then there are companies such as Google, IBM Qiskit is actually based on this superconducting loop. So they are using superconductings as a qubit. Lot of people want to go towards silicon quantum dots as well as a qubit. Why? Because in the previous talk I told you that all the fab labs where in the foundries fabrication is happening for the chip, they all are silicon based. So we have a lot of information available about silicon foundries, and these foundries, we know how to etch, how to clean, and that's why they want to use silicon as a material. Similarly, you can also use diamond, but this will be quite costly. So lab grown diamonds is also there, but the device cost is quite high. But up to now, you know that okay, there are different systems. Based on that, we call different kind of quantum computers. So in today's talk, what we will talk about is photonic based quantum computer. So photonic quantum computer. And if you want to create a photon based quantum computer, you require three major things. The first thing you require is a source where the photons can be created. We call it a single photon source. The second thing you require is a detector. We call it a single photon detector. So if you remember, in the previous talk, I have given you idea about superconducting nanowire based detectors or single photon detectors. They are called SNSPDs, or you remember maybe about the avalanche photodiode. So they can also be used as a detector to detect single photons. Now, in order to manipulate your quantum state, so manipulation means you want to apply some sort of logic gates. So in classical, we have AND gate, OR gate, NOR gate. Similarly, in quantum, we have Pauli X gate, Pauli Y gate, Toffoli gate, Hadamard gate, CNOT gate. So there are different kind of gate operation which you can perform on a single qubit or double qubit. And using these things, you can manipulate your quantum bit or your quantum system. So this manipulation is being done actually using Mach-Zehnder interferometers in case of photon-based quantum computers. So here is a schematic. Suppose if you want to create a chip, and on this chip you want to do your photon-based quantum computing, right? So what you require is a source. Here you start with the source. Then you require multiple detectors where you can detect single photons, and this circuitry here, this circuitry will be using a lot of optical components. For example, building Mach-Zehnder interferometers to do filtering, to do modulation, and all those things. So you will also use mirrors, beam splitters, or multiple things. Focal cell is like electro-optic modulator. So multiple optical components are being used here as well. To do what? To manipulate the quantum state of the system. So that is the basic idea. Now let me show you a paper which is 2019 publication, and in this publication they have done a computing problem which is called boson sampling, and what they have used is they have used 20 photons. So finally this is how the system looks like. So you have a quantum dot. This quantum dot is sitting inside a micropillar cavity, and lot of single photons are getting out. So here single photons are coming out and they are getting into this complete optical system. So by deplexing, what you can create 20 photons at the input. So here you have roughly 20 photons available, and here you have 60 single photon detectors. So you have multiple SPAD, 60 SPAD available here, and that is the optical circuitry, so the Mach-Zehnder circuitry, which will transform your optical quantum state. So as I said in the beginning, so this is not, it is very vague. I just simply explained you the whole thing, but this paper is quite important and interesting. So the three major components required is a single photon source. So this part where you can generate a single photon source, the detector part where you can detect it, and the in between you have to do all the optical transformation what you would like to perform. And this is a basic example of a photon based quantum computer. So photon based quantum computing is done here, and what kind of experiment was done? Not Grover search or something else, but they have done a boson sampling. So let's go one by one to the main component of it. So as I told you, what we require is a single photon source. What do I mean by a single photon source when I talk about photons? So suppose I have a gun and I have a detector here, and I click the gun and a single photon comes out, and then I detect it. I click again, again a single photon comes out, click again, single photon comes out. So as as soon as I click, I want only one single photon. I do not want two photons. I do not want zero photon. That is the meaning I have a single photon source. What are the other characteristics there so that I can call it as a single photon source? So what are these ideal properties? I will make a list of it and then we will go through it. So the very first thing is that only single photon should be emitted. Once you trigger, only one photon should come out. How do I prove it? So there is a method called HBT interferometry. If you perform this interferometry, you can prove that you really have a single photon source. What you do in this interferometry is actually measuring the photon statistics. Okay, that is the first thing. So this is called Henbury, Brown and Twist interferometer. The second thing, whatever the photon coming out, they should be indistinguishable. What is the meaning of that? So the first photon should be exactly same as second or third or fourth or fifth. So all the photons should be identical. There should not be anything by selecting that you can say that, oh, photon number 5 is different from photon number 7. So they all should be identical. How do I prove it? So there is an interferometry called HOM interferometer or Hugo Mandel interferometry. By doing that, you can prove that you have indistinguishable photons. The third thing is that you should be, so that's more like detector thing, but you should be able to detect them with a near perfect efficiency. So it's not like there is a single photon but you are not able to detect it, or you detect out of 10 you are only detecting 5 of it. So the detection should be with near perfect efficiency. Next is the wavelength tunability. So if I need a single photon at 500 nanometer, I should be get it at 500. If I need it at 800 nanometer, the device should be in such a way that I should be able to get it at 800 nanometer. The next is that it should be operable at room temperature. So the most desiring thing is that your device is working at room temperature. You do not require any liquid helium or nitrogen to cool it down. If you remember this SNSPD, superconducting nanowire detectors, you have to cool it down at 1 to 4 Kelvin temperatures. So these kind of things is usually impractical. You cannot make a device or laptop or something which you can roaming around with temperature of 1 to 4 Kelvin maintenance. The second thing required is the site selective placement. So for example, this single photon source, I want to place it in front of a waveguide or in front of a Mach-Zehnder interferometer. I should be able to place it in front of that thing. It should not be that the site selectivity is not there. The next is the brightness. So source should be very bright and the repetition rate should be high, meaning the first photon is coming out, then after a 10 to the power minus 6 second, the second photon comes out. If that is happening, you have a megahertz of repetition rate. But if within a nanosecond, the next one is coming out, then you have gigahertz source. Repetition rate should be very high. How do you do that? So there is a thing called Purcell enhancement. So what you do is, for example, you take a quantum dot, you put it inside a plasmonic cavity. This cavity will enhance the repetition rate and also it will enhance the brightness. So there are ways by which you can achieve each of this objective, right? But what is happening in reality is that such a source doesn't really exist. So there are always drawbacks in the things, and suppose you will not be able to get a single photon where the HBT interferometry is proving that it's a single photon. What do I mean by HBT interferometry? This we will discuss in next slides. But people are working in this direction to create a pure single photon source which is deterministic, like on demand things are available, and such a thing at the moment is not there. So now let me give you some example, like what things can be used as a single photon source. So here's the first example. So colloidal quantum dots, you can use them as a single photon source. So for example, this is a quantum dot, that's a TEM image, and one of single of these is a quantum dot 5 to 7 nanometer, and they are made up of using chemistry methods. So that's why the colloidal quantum dots. Second thing which you can use as a single photon source is an atomically thin 2D material. So in this case, this is hexaboron nitride. That's an atom thin layer. If you create one defect at this location, this will act as a single photon source. That is the second material you can use. So you can use quantum dots, you can use 2D materials. Third is you can use epitaxially grown substrate as a single photon source. So there is a technique called molecular beam epitaxy, and you can grow quantum dot using that method. So one quantum dot is here, second is here, and the difference from colloidal is that this is done by using chemistry. It is cheap and the quantum efficiency is lower, but here the quantum efficiency is high. But this technique demands a lot of money, so the machine itself is quite expensive. Depending on the same technique, molecular beam epitaxy, I will show you one example. So here is the indium arsenide quantum dot sitting here. This is might be 10 nanometer. So the thickness of your hair is in microns, and you see that is 1000 times smaller than that. So 10 nanometer quantum dot sitting here. you come up with a laser pulse, and then finally the pulse will interact with this, and then it goes out with single photon. So finally you can also use color centers or diamonds, lab grown diamonds, and then this is the structure. And if you create a vacancy here, so this vacancy will act as a single photon. So similarly, what you are doing in the 2D materials, you can also do the same thing in the color center, and then you have a single photon source. So up to now, what we have studied is that quantum computer can be made using different methodologies. You can make ion trap based, atom based, you can make photon based, superconducting based, or topological charge based quantum computer. So multiple type of quantum computer can be made. Out of that, we selected for photon based. And in the photon based, there are three important things. First is the single photon generation, second is the detection, and third is the manipulation. So now we are only talking about the single photon generation and what kind of materials in this world which are there, which we can use as a single photon bit generation or single photon qubit. So now let me tell you how we can go about the purity of it, or this HBT interferometer. So I told you, if we have a single photon source, the very first characteristic we have to prove is that we have to do the HBT interferometry. What is this interferometry? So suppose you have a quantum dot. This quantum dot is a absorption will happen as a two-level system. So you have to pump it, right? And then it will emit as the photon. Photon will come out from the quantum dot. So this is how the typical spectra of a quantum dot looks like. So this is the absorption, right? This is the absorption profile, and these are the emission profile. So if the quantum dot size gets bigger, the emission will shift towards the higher wavelength, or redshift will happen. So for example, a 3 nanometer diameter quantum dot emits 500 nanometer, then if we have a 6 nanometer diameter of quantum dot, then it might emit 550 or 560. And if you keep increasing this diameter, the wavelength of emission will shift towards the higher wavelength. So that is the case of this quantum dot. Now suppose you have a quantum dot which is sitting here, and this quantum dot is giving you single photons, right? But first you have to excite this quantum dot. So you have to use somehow, let's say, some laser at close to 500 nanometer to excite it, and you excite with the 532. So green laser, the laser goes like this. It gets reflect from this DCM, which is a dichroic mirror. So what is the meaning of a dichroic mirror? Is that green light cannot transmit, it can only reflect, and red light can only transmit, it cannot be reflected. So green can only be reflected, so green gets reflected, it's code going down, and then it excites the quantum dot. Now quantum dot emits red light which comes out and pass through this DCM, because red light can only be transmitted, it will not get reflected. So the red light is passing through, it reaches a beam splitter, and now it half of it can go here and half of it can go here. But we are talking about a photon picture, so photon cannot become half and cannot go to the detector 2 or detector 1, right? So if you have a single photon, either it can go up or it can go here. So either the transmission will happen or the reflection will happen, right? So let's say you have this, so I take this thing here. So you have the beam splitter and a single photon is coming. Now the single photon has two options. If it is transmitting, then this detector will click, and if it is reflected, this detector will click. But there is no way possible that both of these detector can click at the same time. So if you really have a single photon source, the probability of clicking these two detectors simultaneously is zero. That is the main principle of this HBT interferometry. Suppose you do multiple measurements, and at zero time delay, so there is a delay machine here at zero time delay, meaning both the detectors having no time delay. So there is always a zero chance that both the detector can click at the same time, because it is not possible. If a single photon is coming with zero time delay, either this will detect or this will click. So the probability to detect both the detector at 0 time delay will be equal to 0. So this value will go close to 0. So if G2 tau is 0 at 0 time delay, then you have a single photon source. That is the main criteria and the main method people try to use to prove that they really have a single photon source. Suppose they have multiple photons, then what happens? That some of the photons will go to this detector or some might go to detector 2, and then 0 time delay both the detector can click at the same time. So there is always a higher probability or roughly one probability. So this will become a straight line, right? If it's a multi-photon source, not a single photon source. So that is the very first methodology, which is HPT interferometry, to check whether we have a single photon source. You can now use, rather than a quantum dot, a 2D material or a vacancy of diamond, and then they all will give you the similar G2 values, meaning at 0 it will go to 0. Now look at the second picture. So what we wanted is to check the indistinguishability. So this is denoted by term neta, and we have to do Hugo-Mundell interferometry. What this interferometry tells is that suppose you have two photons and they both are identical in all way possible, and then they comes on a beam splitter, then four possibilities are there. Either this will get reflected and this will get transmitted, so both will leave the port together. The second possibility, the left one can transmit and this one can reflect. Again, the both will go or leave the beam splitter together. The other two possibilities, that one get reflected, one get transmit, or sorry, both get reflected or both get transmitted, meaning both will go to other direction from the beam splitter. So in these two cases, only one of the detector will click, right? So only this detector will click. And in these two cases, both the detector will click. This will also click and this will also click because the photons are available in both the arms. So if this happens, this is called a constructive interference, these two situations. And if this situation happens, this is called a destructive interference. And there is a term called fringe visibility, which is defined by V. So if constructive interference happens, fringe visibility value will be 1. And that we call the indistinguishability. So it will become 1. If destructive interference happens, then this value will become 0. So what we want is that this value should always be 1. Then we will say that we have the photons which are indistinguishable, meaning you cannot distinguish between this photon and this photon. They both are identical, they both are same. Not only these two, but whatever the photons are coming from this source, they all are indistinguishable. Now suppose you put an electro-optic modulator and you change this photon somehow. So now these two photons are not same. Then this kind of situation will arise and both the detectors will click. So then your indistinguishability value will be somehow close to 0, 0.1, 0.2, and which is not desirable for quantum computing. So this is briefly all about the single photon sources, like what kind of sources you need and what are the characteristics you have to look for in a source. Now let's go into the detection part. So we are not talking about the detectors. You will see we are talking about the problem with the detection. Detector is already there and there is information about the detector that either you are using avalanche photodiode or you are using a superconducting nanowire based diode, but you will see what I am saying with the problem with the detection. So there are some challenges how you detect single photons. So remember, in previous classes I told you the energy of a single photon is roughly 10 to the power minus 19 joule. So this is roughly minus 19 joule, and you can assume it's a very small amount of energy and you are trying to detect it. And the noise level at room temperature is also roughly at the similar level, so 10 to the power minus 20 joule or something. So signal to noise ratio becomes very tricky. You don't know you are detecting single photons or you are detecting a noise, right? Other than there is a very small amount of power or energy, what are the other problems? So have a look. We have an, so how do you see to a photon or light, usually we use a microscope, and in the microscope you always have objective lens. So consider this as an objective lens. Now assume that you have a quantum dot in a bulk material. So you will pump the quantum dot and then light will come out in all possible directions. And very small amount of light will go towards your objective lens in this direction, right? So the problem is that your efficiency of collecting the light is quite poor. Even though the light is coming out, but it is not going in the right direction, which is the direction of the objective lens. You want all the light to go in this direction, right? So that is the problem. And you are roughly collecting only 0.01 of the total power. So how to solve this? So the idea is that you take this quantum dot and put this quantum dot inside a micropillar cavity or use some sort of antenna. The job of this antenna is to direct the light from the quantum dot in this particular direction so that most of the light goes to the objective lens direction and then we can collect it. So the aim is to collect most of the light, whatever we can collect, most of it from the quantum dot. So what is the problem then? So the problem is that there is always a coupling efficiency. So here is the quantum dot. What you want is, first, the light from the quantum dot will get coupled into this antenna or micropillar. So there will be the first coupling, which is beta, that how much light is getting coupled into this antenna. Now out of this antenna, how much is going into the lens, that is the coupling efficiency of gamma. So the total coupling efficiency becomes gamma multiplied by beta. So that is the total coupling efficiency, and you have to optimize your system in such a way that most of the light is transferred into this antenna in this direction, and out of that mode, which is this optical mode, antenna mode, this mode has to couple into the lens so that we can capture most of the light. So that is about the coupling efficiency. So this is one of the problem in order to detect the single photon source. So detector is doing its job. We are not discussing about the detector. What we are discussing, how to take these single photons to the detector. In between also there is a lot of optics involved. And this optics loses the energy because it's already very small amount of energy, and this, if this energy gets lost, we are anyways not detecting anything. Then comes the second problem. So suppose you have a quantum dot, right? And what we know is that in the quantum dot there is a valence band and then there is a conduction band, and usually we pump the system so electron goes up, right? And then once it comes down, so it goes up, and when it comes down it emits a photon, right? And we can here is the CCD count, and then we can write down the energy in terms of EV, the photon which is coming out, and then this is the zero phonon line. So here is the wavelength of the photon which is available, right? But this is the very ideal case. Actually, quantum dots not only have the conduction band, but they also have surface defect or trap state. So if you remember in the photodiodes lecture also we talk about the surface defect. Now what could happen, rather than this electron going down completely to valence band, it can first go to the trap state. And then from the trap state, it will come back to the ground state. So when this happens, the photon will be emitted not with this much of energy, but at some other energy. So the photon emission will not be like this, but it may be emitting here or here or here. So because of these extra trap states, there is always a band, and this is called phonon sideband. The problem with this phonon sideband is that all the photons which are emitted by this phonon sideband, they are incoherent in nature and they are distinguishable. But what we want is coherent photon and indistinguishable photon. So this zero phonon line is desirable because here all the photons are coherent and indistinguishable, and 90% of emission happens like that. But this 10% of emission is there which creates the problem. What kind of problem? So you might have heard about the error in a quantum system, or whenever we try to measure something there is a decoherence problem. So these kind of things which are there which created decoherence or the error into the system. So suppose you are running a code and then suddenly there will be a lot of errors into it, and these are the things which create these kind of error in a quantum system. So I hope up to now, at this point, it is clear to you. So the third challenge is the scalability issue. So we do not want a single qubit or 2 qubit or 10 qubit, because if you want to perform a complete logic operation, you required multiple qubits like 30, 40 qubits. So in this boson sampling example I told you, they really used 20 single photons. So what we required is multiple single photon sources. Now let me give you some example. So SPDC, this is a process, again a process which you can use to generate single photon. And here is the value for each of these processes. This is the value of indistinguishability and value of efficiency of detection. So the efficiency of detection is quite poor in this case. Second is the bulk quantum dot, and third is the quantum dot sitting inside a antenna or pillar structure. And in this case, this is the indistinguishability and this is the efficiency. Now, any of the photonic based quantum computer if you are using, then suppose you have you have an oracle or some code, and if you want to perform this operation, so the success probability of this experiment is defined by this equation, that how much will be the success, where n is the number of photons involved or number of qubits there. So you can take a logarithmic both side and then you will end up here. Now suppose I fix the value of p, that I am doing an experiment and I already want a success probability of 10 to the power minus 7, let's say. I already want the success probability. You will say that it's a very low. I want a success probability of 1. But let's try to first start with the success probability of 10 to the power minus 7, that there is only this much of probability that you will succeed. Now you know the value of p, and for all three cases you know the value of neta and epsilon. So you put these values and you try to plot a curve of number of qubits required versus the multiplication of epsilon and neta. In case of SPDC, what you will observe is that what you require is roughly 3 photons with a probability of 10 to the power minus 7. So you really need to increase this number if you really want to have a good probability. And in case of this quantum dot, what you could see is that this number is 4. And once you place the quantum dot inside a pillar, this number reaches to 30. So you could see that this is 0.6 multiplied by roughly 1. So this is 0.6 here. And you can calculate how many number of photons are there. So this might be roughly 30 photons. And when you talk about quantum supremacy, what you want is roughly this value tends to 0.99 and this value also tends to 0.99. And if you put these value, and if you want a success probability of 10 to the power minus 7, you will have roughly 800 qubits. So that is the main challenge right now, is that number of qubits are very less and we need to increase number of qubits, and we have to reach at least number of 800 or 100 or 500. So I hope up to this point it is clear. So now let's go a little bit more deeper into the photonic based quantum computer. So as I told you, there are three things which are required. First is single photon sources. Second is the Mach-Zehnder interferometry or the optical components in order to require the quantum state manipulation transformation. And the third is the photodetector. So for single photon sources, the first option is you can use SPDC based single photon sources. I told you the efficiency for these are quite low, but you can take a different kind of crystals, BBO crystals, and then you can generate signal and idler, and then you have this entangled single photon source. The second is to use these quantum dot which are sitting inside a micropillar cavity. So these two options I already explained you. Now for the second option, in order to transform the qubits, either you can use free space optics, or you can use fiber optics, or you can use integrated optics. So there are three options available here. Let's go one by one. What do I mean by free space? You can use lenses, mirror, beam splitter, all these things. And suppose this is the algorithm for Grover search, right? And if you want to implement this algorithm, this is how the setup looks like for optical qubit based quantum computer. So it's a quite a coarse setup. And if you increase your depth of your circuit, then the setup can go up to like this. Now the problem is that that's again the scaling problem. So as soon as you start increasing number of bits and you use free space optics, meaning you use optical table and you try to put things on top, if one of this mirror is misaligned somehow, then your whole system is gone. So you will have very hard time finding it out. So that is the very first problem. And 6 qubit based quantum computer has been shown in India from ISC Bengaluru. Professor Chandrasekhar's group has showed it. But in order to scale it, I think there might be some challenges in this regard. The second option is to use fiber optics, but with the fiber optics is that losses are very low at telecom wavelength, but at the other wavelengths, there will always be a problem with the losses. The third option is to use an integrated optics, meaning to use a chip. So suppose you have everything on a chip. What do I mean is your single photon source, your detector, and all the optical things like such as mirror beam splitters, which you can create using some sort of ring resonator or Mach-Zehnder interferometers. You can produce these things on a chip. So that is the integrated optics. And in this, you do not need very bulky setup of the optics on an optical table. So in this regard, let me show you an example from my research that how we are trying to create a single photon source on a chip. So the idea is something like this. We have a silicon wafer and then we have a waveguide on top. And I want to place a light source here, and most of the light should go towards the waveguide and very less light should go in all other direction. And the light source should be guided inside this waveguide, and finally we will detect it. So that is the whole aim or the idea, to make a light source on a chip in front of a waveguide. And the wavelength of this light source should be 650, 900 and 1500 nanometer. And we would like to use quantum dot for this purpose. The next is, these two will not work because quantum dot usually will emit unpolarized and light will go in all possible directions. So we need to place an antenna. And this plasmonic moon shape, half moon shape thing will act as an antenna. Now antenna shape can be different. So there are three possible options you can make. So we have done the simulation. That's why we opt for this particular antenna, and we will use this antenna because this helps to guide the light in this direction. So we will go for this and let's try to make this nano antenna. So first we will try to make things on a glass substrate. So we take the glass substrate, we deposit gold, silica and gold layer on top of the glass. On the side we have these polystyrene particles, and we will make a layer of these polystyrene particles inside a beaker. So that is the diffraction color what you are seeing here. And finally we pick this monolayer on the top of our substrate. So this is how it looks like. And then we reduce the size of these PS particle by oxygen. So we shrink them, and this is how it looks like. And now there is opening in between since there is gap. So we use argon H and we remove all the gold, silica gold from the areas where it is not available. The PS is not there. And where the PS particle is there, the underneath things are protected. And finally we take some solution THF and we remove these particles, and this is how the structure looks like. So you have your nanoparticle or your antenna which is available here in 2D hexagonal format, right? Then we try to make a layer of quantum dot. So what we do is we take a beaker, we put diethylene glycol in it and put a drop of quantum dot and then let it evaporate on the surface here. And finally we place our substrate and pick the monolayer of the quantum dots. So what we are trying is to have these antennas, and then we try to place our quantum dots here. And what we want is that light should go in this particular direction. Here is the waveguide sitting, and most of the light should go through the waveguide, and here we will detect it. But there is a lot of quantum dot. We wanted to make a single photon source. We don't want to make multiple photons here, multiple quantum dots, but we will talk about it. In the beginning I will explain you multiple quantum dots. So this is how the structure looks like, and if you look in with the some SEM image, this is how the sample looks like. So you have these antennas and lot of monolayer of a quantum dot is sitting there. This is how it looks like. So I showed you everything on a glass substrate, but similar thing, you have to believe me, can be done on a chip. So this is the hierarchy, how this method works. So you have a chip, that is the side view of the chip. This is the waveguide, both side. And then you can place your antenna and the quantum dot in between. So finally, this is how the chip looks like. That is your chip. And these are the areas where you have created these kind of light sources. So if you look with the microscope, that's the top view. That is the silicon nitride. In this direction, this is silicon nitride. These are the areas where your quantum dot and nanoparticle antennas are sitting. So within this region, your antennas are sitting. And now you want to see whether light can go in this direction or not, right? So if I zoom in those areas, this is how you can see that this is silicon nitride here and here, and there are quantum dots together with the antenna. It's sitting there. This is how it looks like. Once you place the quantum dot on top, what you could see is that you have created a light source which is emitting 630 nanometer or 650 nanometer, because that was the emission of the quantum dot. So you have a light source in front of a waveguide where red light is coming out. So that's just simple fluorescence microscopy imaging you can do, and you can prove it that there is a quantum dot. So they are not available in these regions here, but they are specifically available in the gap. So exactly here, they are not everywhere. So exclusively we have pinned them down here. Okay. So now next comes is the how much is the coupling. So you have placed your antenna and the quantum dot in front of the waveguide. How much light is getting coupled? So if you look at around 630, 640 nanometer, we have roughly 25% or 20% coupling for the simulation. So we have simulated it, not the experimental part. So simulation shows that there is only 20-30% coupling for a light of 630 or 600 nanometer. Now what we do is we break this chip from one end and we shine the light from the one side, that is the input fiber. It will shine the light, and from the one side we try to collect the light. So this is roughly from where we see how much light is coming out via this fiber, and from this fiber we incident the light. So the very first experiment is only with the quantum dot, so without any antennas. And what we see is that in the CCD the count is roughly 200. So for 640 nanometer count is only 200. As soon as you place the antennas together with your quantum dots, what you see is that in your CCD the count is roughly 1000. So you have 5 times enhancement in your light, meaning more light is now coupled in this particular direction. And this you can do by scanning your fiber here in this direction, right? And E3 means the cavity which has a width of 3 micron. So as compared to only quantum dot, now we can place antenna here, and this will guide the light in this direction, and we have more light coming out. E5 means a cavity of 5 micron width. So you see in this case we have roughly 200 count again, but as soon as you put antennas close to these quantum dot, this count is going to 7 times increasing. So this kind of one point excitation, another point detection mechanism you can use in order to prove that these antennas helps to make a light sources on chip. Now comes the main part, that can we make a single photon source on a chip. So here is the quantum dots. So this is PBS quantum dot. They usually emit around 1550 nanometers, so telecom range, and the size is roughly 3.2 nanometer. And this is the one single quantum dot you could see here, or you could see here. Now that is the sketch where this is the waveguide, and you would like to place a single quantum dot here, right? So if you do it in reality, there will not be only single quantum dot, there will be sometimes 3 quantum dot, sometimes 2 quantum dot, and multiple times there will be single quantum dot as well, right? So now if you look at this particular region, if you zoom in, so in this cavity there is a single quantum dot sitting. So by cherry picking we can find out regions where a single quantum dot is there, and now it's our job to prove whether this is a single photon source or not. And in order to prove this, what we do is we have to do the G2 measurement. But how we have created this? So this all has been done using E-beam lithography. So with the E-beam, you first create a waveguide, and then you create a hole here, and then you simply spin coat your quantum dots on top. And finally, you have multiple dots in some area, and some area you have a single dot. You look with your microscope, and then you find the regions where you have a single dot, and you try to do your HOM interferometry or HBT interferometry to find out whether you have created a single photon source or not. So once you do that, so what is happening here? I'll explain you again. So your quantum dot is sitting here. You take one laser and you excite your quantum dot. So this excitation laser is here. Laser comes in and then it goes like this. It excites your quantum dot. Now this quantum dot will emit some light. So this light emission goes up through this fiber, and then it goes here into this beam splitter. Now there are two SPAD 1 and SPAD 2, meaning avalanche photodiodes. So these are avalanche photodiodes, two photodiodes. And again, both of these detector will not click at the same time at zero time delay if there is a single photon source. So at zero time delay, if G2 tau value is going to zero, meaning you have a single photon source. So if you look here, this value is roughly 0.3. So that means you have a single photon source which is not very pure. So you have to make it even more pure. So if it really goes down up to here, then you have a pure. So it all depends on the purity. But if you go below 0.5, people started to call it as a single photon source. So how pure is it? That depends on the value of the G2 tau. So with this, I am at the end of my lecture for today. And if you have any questions, please feel free to ask. So in order to introduce your delay, so you can have focal cell. So let me go back to my slide. So how do you introduce delay? So here you could see, so in this boson sampling example, what they are using is a focal cell. So what is a focal cell? Focal cell is a device where you apply, so it's a device where you apply the electric current, and then there will be changes in this material, and then finally you can apply some sort of phase delay. So that's a device, electro-optic modulator. So there is some sort of material is there, maybe lithium niobate or something, and then if you apply some electrical signal, the refractive index will change for ordinary and extraordinary light. So once the refractive index is different, the light which is propagating in this direction feels a different refractive index, and light which is propagating here will feels a different refractive index. And finally what the light comes out will be with a different phase delay. So by applying different sort of voltage or electricity here, you can control the phase delay in these kind of circuits. But this all you have to keep in your mind when you are trying to write the algorithm, like I showed you for the Grover search. So when you have this circuit or algo, together with the circuit, you have to make this circuit as well, like which kind of focal cell, how many focal cell, and what kind of voltages and which phase delay are you going to introduce in your line. That is one way. The second way you can see here, so the fiber is getting circulated around something. So by introducing extra path also, you can create the delay into your circuit. So that might answer your question. Okay, so if there is more questions, please write into the chat.
I think there are no questions till now.
Yes, I think I also don't see more questions.
So I encourage participants, like if you again, this is again unfortunate, like you are not posting any query or any question. So it is not possible like you are understanding everything. So again, I request if any issue, any problem, any doubts, please feel free to write in the chat box so that we can respond accordingly. But
So there
as
is a one question in the chat box. Please tell me the laser wavelength for photonic QKD 850 nm or 550 nm or 1550.
I think okay, so actually telecom wavelength is close to 1550 nanometer. So if you would like to do QKD, I would suggest going to 1550 nanometer. So because a lot of fibers are also involved in this, that's why you use 1550. If you have something, suppose a waveguide where you can make a long enough waveguide, you can also do quantum key distribution at 850 nanometer or 550. But the problem is that all your fibers are available at that wavelength. So long distance QKD would be 1550. So using attenuator, it is not, so you can create a single photon source, but it will not be a real single photon source. So what you are referring is, let's say we have a laser and we put lot of filters in front of a laser and we try to dilute it or attenuate the intensity of the laser. But the problem is that the source itself, it has a distribution, and this distribution is, it's a coherent light source, so it will follow a Poissonian distribution. And if you remember from the last slide, what I explained you is that if you really have a quantum light source, so this is a Poissonian distribution, you really need to have a sub-Poissonian distribution, then you can say it is a quantum light source. So just attenuating a laser will not create a single photon source. This will just analogous, which simulation software uses fabrication of circuits using photonic quantum bits. Sorry, this I don't know what I have used. This is a FDTD based simulation, but I think this what you are asking is doing these kind of simulation. So for this, I think photonic integrated circuit based simulation software would be better, but I do not exactly know the name of it. But what you can do is search for the software which can simulate photonic integrated based circuits. So there it will be possible to simulate all this. Yes, yes, you are right. So the other option is using variable attenuator. So you can use it. That is a one way, but it will not be, it will still be a Poissonian source. So you cannot go below short noise limit. So always that will be Poissonian distribution. But yes, it is a way to do that. Yes, I think D wave provides it. Yes. Yes.
any other queries?
There are no queries. I think
Oh,
they know that other two sessions are already coming in the third week of the, so I think they will interact in the next sessions also.
oh, okay, no problem. So if there is no queries, let us thank the speaker, Dr.
Thank you,
Vaibhav
sir.
Gupta, for your talk. And still, if there are any queries, I again ask participants, please feel free to ask him during his next lecture. So once again, thank you all the participants for joining today, and particularly our speakers, Dr. Aswad Babu and Dr. Vaibhav Gupta, for their valuable time and the talk. Thank you.
Thank you, sir. Thanks a lot.